Welcome back. In example 2, we have the integral of dx over the square root of 4 plus x squared. So what are we going to do for our trig substitution here? If you said let x equal 2 tangent theta, that would be correct. And here I'm going to go ahead and write the interval, which is negative pi over 2 to pi over 2, not including the endpoints because tangent is undefined there at the endpoints, negative pi over 2 and pi over 2. And I should pause and mention actually that you can try other techniques. First, if you can do like a regular substitution, then you can try that technique. If you want integration by parts, you can try that. But if you run out of options, and especially if you see that radical of either a squared plus x squared or minus or switched around, that gives you a clue that trigonometric substitution is one way to try to handle these problems. But definitely look for those other methods first. You could try thinking, well, what if we let u equal 4 plus x squared? Then the du would be 2x, but I don't really see an x here with the dx, and I can't really make an x here with the dx without creating another one somewhere else. So regular substitution doesn't look like it's going to work out here. And you could try integration by parts, but it's kind of hard to know, if you think about taking, what would you let u equal to? And if you take the derivative of that, is that really going to be looking simpler? You could give it a try. It's definitely worth it. Integration, there's not really like this is the correct technique for all these integration problems, but there are some problems where it is much easier to do it one way compared to another way. And so if you see those radicals, you might be thinking about trig substitution unless you can find another simpler way. All right. So here we're going to let x equal 2 tangent theta. So we have dx will be 2 secant squared theta d theta. When we take the derivative of tangent, remember it's secant squared theta. And when we make all the replacements, we get the integral of 2 secant squared theta. That's the dx that I'm going to put on the top. I'll put the d theta out there as a reminder, so don't forget that. And then we have on the bottom the square root of 4 plus, now x squared, I'm just going to jump in and write it as 4 tangent squared theta. 4 tangent squared theta. Just to save that extra step of, squaring the x value. All right, so we have 4 tangent squared theta. So now we're going to focus on the radical, try to collapse the radical. So in the radical, we can factor out a 4, and we have 1 plus tangent squared theta in parentheses. Then we can replace 1 plus tangent squared theta with secant squared theta. And just on the side here, by the way, remember that sine squared theta plus cosine squared theta equals 1. That's the basic one to start with. And remember that you can always get those other equations by dividing by either sine squared or cosine squared. If we want tangent squared coming in, we want a sine over cosine, so we want to divide through by cosine squared theta. So sine squared over cosine squared is tangent squared, cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. This just helps you remember what that identity is. So if we see the 1 plus tangent squared, that's going to be replaced with a secant squared. Just a quick little reminder there. So when we take the square root of 4 secant squared theta, we get 2 secant theta. Again, because we made our restriction of theta on theta so that we didn't have to put the absolute value bars around the secant theta. Okay, so now we're going to write the collapsed version of the radical. We have 2 secant squared theta over, and then the collapsed radical is 2 secant theta, and we have d theta. Now there's a secant theta that cancels, and also the 2 cancels. So we have the integral of secant theta d theta. And the integral of secant theta, this was mentioned in a previous video. I'll give that one to you, so we can just write down this is the ln of secant theta plus tangent theta d theta, and whoops, not d theta, plus c plus c. Again, this was a little bit of a tricky integral, and we did it as part of the secant integral of secant cubed theta, you might remember, or x I think we had at the time. But I'll give that one to you if you need it. So here we have ln, the absolute value of secant theta plus tangent theta, and then plus c at the end. Now we've got to go back from theta into x. So let's do that off to the side. Using our relationship between theta and x. And I'll just write down tangent theta equals x over 2, because we initially set x equal to 2 tangent theta, so we can divide the 2 over, and we get tangent theta equals x over 2. Now we can draw a little triangle. A right triangle with an angle theta in it. The opposite side would be x, the adjacent side would be 2, that way tangent is x over 2, tangent theta that is. And then the hypotenuse here by the Pythagorean theorem will give us 4 plus x squared. Now you can write x squared plus 4 inside the radical, or 4 plus x squared. It doesn't really matter either way. So it's the square root of either one of those. But I'm just going to match the original radical that we had started with, which was the square root of 4 plus x squared on the bottom. And that just makes it kind of consistent that way. But either way you write it is fine. So now that we have the triangle all set up, we can evaluate or rewrite secant theta as, well, secant theta is like the reciprocal of cosine. So if you remember, cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. It's the funniest of all trig ratios. Ha 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 ha. All right, so sorry. So then here it's going to be the square root of 4 plus x squared over 2, hypotenuse over adjacent. Then we have tangent, which will be x over 2. Tangent theta is x over 2 plus c. Okay, and you can leave your answer like that if you want. We'll just box that. Okay, next up we've got example 3, which is the integral of dx over the square root of 25x squared minus 4. And this is of the form x squared minus a squared, right? So which trig substitution are we going to use here? If you said secant theta, that would be correct, or a secant theta. Now the only thing is that here it's a little different because we have this 25 out in front of the x squared. So how can we handle that 25? Well, there are a number of ways of handling this actually, but we're just going to go with this way, which is to factor out the 25. If you want to get rid of that 25, just factor it out and it'll be gone. So here we have the square root of 25x squared minus 4. I'm going to factor out the 25 from both of those terms inside the radical. Now when I factor out the 25 from the 4, all I'm going to get is 4 over 25. Remember, factoring is like the opposite of multiplication. It's like the opposite of distributing, which is multiplication. So when you do the opposite, when you do factoring, you're going to have to take a step of dividing each of the terms that you factored stuff out of. So you take whatever you factored out and divide each of those terms to see what's left over. Because if you turned back around and distributed, you'd be multiplying that thing back into all the terms. So we have 4 divided by 25 left over there. Now the square root of 25 is 5, so that can come out of the radical, but the rest of it's stuck inside. And that's okay, because now we've got it in the form x squared minus 4 over 25 inside the radical, and we can deal with that trig substitution now. So we're going to write this radical as the integral of dx over 5 times the square root of x squared minus 4 over 25. Oop, we wrote the dx already. This integral is only big enough for one dx. So now the next thing we're going to do is our trig substitution. The a value here is going to be the square root of 4 over 25, which is 2/5, right? Remember, we want to make the square root there because in a moment we're going to be plugging it into x squared. And so we'll have that thing squared, and it's got to match that 4 over 25. So 2/5 then, and we said secant theta. And here we're going to put the restriction on theta. So theta is going to be between 0 and pi over 2, or pi and 3 pi over 2. Now our dx is going to be the derivative of secant, which is secant theta tangent theta, d theta. And we have that 2/5 in front still, that hangs around as a coefficient. Okay, let's replace everything inside of our integral now. So we have our dx turned into 2/5 secant theta tangent theta. I'll put the d theta off to the side. And then over the square root, 5, the square root of, and I'm going to, again, like the last one, just square it. So we have 4 over 25 secant squared theta minus 4 over 25. Okay. Time to collapse the radical. Let's take that radical, factor out the 4 over 25 inside, and we get secant squared theta minus 1. Secant squared theta minus 1 is going to be equal to tangent squared theta. Let's just take a peek up at example 2. So secant squared theta minus 1 gives you tangent squared theta. This again comes from that Pythagorean identity with tangent and secant in it. Okay, so then we have the square root of 4 over 25 tangent squared theta, which gives you 2 over 5 tangent theta. Again, we can drop the absolute value bars because here on our interval, tangent is positive. In the first and the third quadrants, tangent is positive. Okay. So here, I'm going to leave that 2/5 up on top. So we have 2/5 secant theta tangent theta. On the bottom we have 5 times 2/5 tangent theta d theta. The 2/5 are going to cancel, which is nice. The tangents will cancel. So really we just have 1/5, which we can pull out of the integral, and then times the integral of our old friend secant theta. Hello, secant theta. All right. I don't know where that came from. So we have secant theta, so that one we might remember is ln times the absolute value of secant theta plus tangent theta plus c. And then we want to go back into x, so we can use that relationship that's set up between x and theta. Remember that it was x equals 2/5 secant theta. So if we multiply both sides by 5/2, we get secant theta equals 5/2 x. Or I'm going to write it as 5x over 2. Then we can draw a triangle, a right triangle with angle theta. And if secant theta is 5x over 2, this is the reason we put the x up on the top of the fraction, so that we can think about the trig ratio as a fraction. So there's like a top and a bottom. And so secant, remember, was the reciprocal of cosine. So secant had hypotenuse on the top and adjacent on the bottom. So hypotenuse is going to be 5x, adjacent is 2. And then the other side, the third side of the triangle, is going to be the square root of 5x squared, which is 25x squared, minus 2 squared, which is 4. Notice that we ended up with that same square root, the square root of 25x squared minus 4. That's going to happen in these trig substitution problems. Okay, so we then have secant theta is 5x over 2. So we have 1/5 ln absolute value of 5x over 2 plus tangent theta. Tangent theta is opposite over adjacent, so that'll give you the square root of 25x squared plus 4 over 2. Close the absolute value, put a plus c, and box our answer. But wait, there's more. So even though we went all the way down to x and we boxed our answer, and that's totally fine for an answer, I did want to point out one thing that you might see in a solutions manual, for example. You might see that the 2's suddenly go disappearing. You might wonder, where in the heck did the 2's go? The 2's on the bottom of these fractions inside the natural log. They'll suddenly disappear for seemingly no reason. Well, here's what could happen to them. Let me write this down below. So I'll write or, actually put this in gray. So or, you could continue simplifying and using some log properties to help you out by writing 1/5 ln of 5x, combining these two fractions, 5x times this plus the square root of 25x squared plus 4 all over 2, and then close the absolute value bars, put the plus c. And now what we could do is use a natural log property. We have the log of a quotient is going to be equal to the log of the top minus the log of the bottom. Right? We have 1/5 times the quantity ln absolute value of the top, which is 5x, plus the square root of 25x squared plus 4. Oops, that's a minus 4, I'm sorry. And then close the absolute value bars, and then we have minus ln of the absolute value of 2 plus c. And then what we could do is distribute the 1/5. So we have 1/5 times ln of the absolute value of 5x plus the square root of 25x squared minus 4. Close the absolute value bars, and we have minus 1/5, oops, minus 1/5 ln 2, the absolute values don't really do anything there, plus c. And now here's where the book is going to get rid of the 2. This is where the 2 disappears. So if you think about this last part right here, minus 1/5 ln 2, that's just a constant. So if you write that thing plus c, well, c is any constant as well. So rather than writing this constant plus some other constant, you can just rope these constants together into a single plus c, or you can use plus k. A lot of times the back of the book will, or the solutions will write just plus c, so they'll reuse the plus c and just write plus c again. This is going to come up again when we tackle Chapter 9, differential equations. We're just going to rope in any kind of constants that are added to our other constants and just call them a single constant. I mean, after all, if c can be anything here, well then negative 1/5 ln 2 plus c can be any constant as well. So might as well just call this whole thing plus c. So there it's going to just destroy the 2. It's going to absorb the 2 into the constant, and so you won't see it anymore. And you'll just see 1/5 ln absolute value of 5x plus the square root of 25x squared minus 4, close absolute value, and then like plus c, and that'll be it. So I wanted to make sure that you knew to be on the lookout for that, in case you are wondering where that 2 is going, or where that denominator or that extra constant term is going. In example 2, we could have done that as well. We could have brought these fractions together, used a log property to separate out the log of the top minus the log of the bottom, and we would have ended up with a minus ln 2 that could have been absorbed into the plus c. So in essence, making it disappear. It's like a disappearing act. All right, that's it for this part. See you in the next part.